Now seminar number 9, and we'll continue to discuss linear homogeneous equation of the first or of the n or for the n. And now I'd like to consider examples. Okay, task number 1. Find the general solution of the following differential equation. The fourth derivative minus 3y 3 primes, or 2 primes, sorry, 2 primes, 2y prime equals 0. Okay, who wants to solve? Welcome. Equals 0. Now you should guess the right. Maybe you may divide polynomials.
No.
No?
So minus 2 lambda minus 3 lambda. So yes.
I think minus 1 is another root. Negative 1. Negative 1. Negative 1 and 2. Plus 1. Okay, simple roots, right?
Lambda is equal to minus 1, 0, 1, Q. And so alpha.
C1. I think it's better. C1 plus. C2 times. So this is 1, and so we needn't write it. So we may delete it. Thank you. Right. So task number 2 will be the following. So find the particular solution of the following equation. Minus 2y prime plus y equals 0. And given we're given the initial conditions. Okay, who wants to prove or to solve? Welcome. No. All right. So maybe we should explain this solution, right? Is it difficult to solve, or do you understand the method? So first we should write the characteristic equation. Then find the roots. Right. Right, of multiplicity 2.
So the solution is
C2 times x, correct, times 2x,
no, 1x.
1x, right, but just x, you may write x. Okay, is it clear? So this is the first step, to find the general solution. And next we should use the initial conditions to find this constants, because we know that there is a unique function satisfying these initial conditions. And next we need to find the derivative of this, right? So find the derivative and then form the second equation. So we should do it separately. So maybe you can rewrite the general y equals c1 plus and plus c1. C1
is 0.
No, so C1 plus C1 is 0. It is found from right. I see.
So
right.
Okay, so it is
C2. Correct. And substitute 0 for x.
Okay.
It's C2.
Wait,
So no, so it is not. It is 1, right? So C1 is 1.
Oh no.
Right. But we know, so we may add e to x. Just add e to x. Substitute 1 for C1 and plus e to x. Just e to x. And the derivative will be plus e to x here, right? Plus e to x.
0 is plus 1.
So C2 is negative 1. Right. Minus x. Thank you. Sit down, please. And next, now we will discuss the situation when the characteristic equation has complex roots. We will discuss complex roots. Okay. So case number 3, characteristic equation. Has complex roots. Okay. But from algebra we know that fundamental theorem of algebra works, right? Fundamental theorem of algebra. From this theorem, we know that P of lambda has n complex roots, and if P of lambda has real coefficients, then complex roots occur in conjugate pairs. So this means that the polynomial with real coefficients can be represented as maybe lambda minus lambda 1, where lambda 1 is real, right? And conjugate pairs means that if we have a complex root, call it alpha plus e beta, then the other root will be another root will be lambda minus e beta. So we want to find the solutions of the homogeneous differential equation, and we can write the function which will be the complex function. So alpha plus e beta times x, this will be y1, and y2 will be e to the power alpha minus e beta times x. Both functions satisfy the differential equation. We can check this. We can differentiate them. But suppose we don't want to have complex solutions. We want to have real functions. We want to obtain real functions, but not complex functions. But do you know how to deal with the following? Do you know the formula for e to the power e beta x, for example? What does it mean? So beta x, right, beta x plus I sine beta x, right, correct. And 2 to the e to the power e beta x is equal to minus, right, minus cos beta x. So we should substitute minus beta x, and cos is an even function, sine is the odd function, and so it will be this. Okay, and I claim that given these two functions, if we have these two functions, I can form two functions, real valued functions, which satisfy the original differential equation. The corresponding real valued functions will be y1 is equal to e to the power alpha x times cos beta x, and I will prove that this function satisfies the original differential equation. And the second function will be y2 equals e to alpha x times sine beta x. Let's prove that these two functions satisfy the differential equation. And for simplicity, I will take the second order differential equation. Okay. Suppose we have the second order differential equation, a1 times y prime plus a2y equals 0. Then the characteristic equation will be lambda squared plus a1 lambda plus a2 equals 0. And lambda equals alpha plus or minus e beta is the root of this equation. This means that alpha squared plus a1 times alpha plus or minus e beta plus a2 equals 0 Or let's expand this, and we will get the following. The real part, so we can consider the real part of this equation or imaginary part. The real part will be alpha squared, then this will give us minus beta squared. These two terms come from the first term. From the second term we can take alpha a1 plus a2 equals 0. So this is the real part. So if the complex number equals 0, then both the real part and the imaginary part must be equal to 0. So this is the real part. It is equal to 0. The imaginary part of this will be plus or minus e beta alpha 2. In just a moment, plus or minus and plus a1 times beta from here times I equals also equals 0, right? So this means that this coefficient is 0. It follows that 2 alpha beta plus a1 beta equals 0. Having these two equations, so this one and this one, let's show that the first function y1 is the solution of this differential equation. I want to check this. To do this, I need to take the first derivative, the second derivative, and substitute them into this equation. So y prime will be equal to, differentiated, it will be e to alpha x times alpha cos beta x minus beta sine beta x. This is the first derivative. Using the product rule, we can find this. Next, y2 primes. Let's differentiate it again. I will get this. So first, alpha squared cos beta x minus 2 alpha beta sine beta x and plus, so minus beta squared cos beta x. So if we combine terms, we will get, so e to alpha x. We can rewrite this as follows: alpha squared minus beta squared cos beta x minus 2 alpha beta sine and beta x. Okay, and now substitute them into our differential equation. This one. We will get the following: e to alpha x multiplied by alpha squared minus beta squared cos beta x minus 2 alpha beta sine beta x, then plus a1 multiplied by the derivative. Cos beta x minus a1 beta sine beta x, and plus a2y plus a2 cos beta x. So let's combine the functions. So I will collect similar terms containing cos beta x. The coefficient of these terms will be alpha squared minus beta squared plus a1 alpha plus a2 times cos beta x. And the terms containing sine beta x will be also combined. I will get 2 alpha beta minus a1 beta times sine beta x plus. But look at this coefficient. The coefficient is the same as this coefficient, right? But it is equal to 0. This equals 0 due to the first equation, right? And due to the second equation, this is also 0. And so we can see that this expression is 0. So y1, so this function satisfies this differential equation. So likewise, we can prove that y2 is also the solution. Okay, it's not difficult, but now let's exercise with these solutions, with these equations. Let's try to solve the following differential equation. Task number 3. Solve the differential equation y2 primes minus 2y prime plus 2y equals 0. Okay, who wants to solve? Follow. It's your turn. So I will help you. I will help you. Come here, because so you should exercise with this. So first you should start with the characteristic equation. Minus 8. Not 2, but the square root of 4 is, so we should divide by 2. 2.
Yeah, I'm
Only, over 2. Correct. Then form, right, so then you should find e raised to the power 1 plus I, for example. E to the power 1 plus y. Or maybe, right, here's the solution. Right. I will close the door. But if I want the real valued function, what shall I do? I shall represent e to the power 1 plus I x as, so we should, just a moment, I will take my own chalk, so I have this. So the method is to represent e to the power 1 to the power x plus ix as the product e to x times cos x plus I sin x. And then we can split this into two parts, e to x times cos x and e to x times sin x. And so this will be two linearly independent solutions. y1 will be e to x cos x, and y2 is e to x sin x. And then after this we should take the linear combination of this.
What about the I?
So we should so exclude the exclude I, because I want the real valued solutions. If I want any solution, I can leave it in this form, but I will get complex solutions. But if not, we can just a moment. I can explain. So let's write down the answer, and now I will explain why we can omit I, exclude I. So the general solution. Okay, sit down, and now I will explain. So these are two constants, C1 and C2. I will use tilde, so because they are different from our constants C1 and C2. But suppose we write the solution in this form. How can we see the constants? How can we redefine the constants to get this solution? So let's write. So let's rewrite this solution using this formula, and we will get the following: y equals C1 tilde e to x. Okay, e to x is a common factor, and I will move it on the left. So C1 tilde times cos x plus e times I C1 tilde times sin x. Next, plus C2 tilde cos x plus I, so minus I C2 tilde sin x. Next, we can rearrange the terms in the form, so we will combine the terms containing cos x in this way, plus I times C1 tilde minus C2 tilde sin x. And if we rename the constants, so if we call this constant C and this constant C2, we will get our equation obtained in this way. So this is the same. But we should remember that C2 and C1 must be real if we want the real solution. Okay, and so I have forgotten to check whether these two functions are linearly dependent or independent. We must check this, right? So generally, I will use this part of the blackboard. So suppose we have a conjugate pair of solutions, so alpha plus or minus beta I, so I times beta, and then we will form two functions, e to alpha x times cos beta x and y2 e to alpha x sine beta x, and our goal is to show that these two functions are linearly independent, to use them for our solution. So we must show that these functions are linearly independent. Right, we can do this, right? It is e to alpha x alpha cos beta x minus beta sine beta x, and y2 prime alpha x alpha sine beta x plus beta cos beta x, and the Wronskian will be y1 y2 y1 prime y2 prime. It will be e raised to the power 2 alpha x. So this is the common multiple for both y1 and y2 and y1 prime y2 prime, right? And we will have cos beta x sine beta x and alpha sine beta x plus beta cos, so alpha cos. And alpha sine beta x plus beta cos beta x. Well, so the first way is to find the determinant and check that this determinant is not zero at any point. But the next point, the next possibility is to substitute some value for x. For example, substitute 0 for x. Right? And if this determinant is non-zero for the particular value of x, say x equals 0, then by theorem proved during the lecture, it is not 0 for any x. Right? Let's substitute x equals 0 because I don't want to find the determinant. We will get the following. It will be 1, 0, alpha, alpha, beta, right? Okay, so the determinant is beta. But beta is not 0 because we have supposed that this is the complex root, 2 conjugate complex roots. So this means that beta is not 0. Because otherwise it is real, right? But our assumption that the roots are complex, so beta is not 0. So the determinant, the Wronskian, is not 0. Right, so they are linearly independent. Okay, and so this is the general solution. Now I'll have a look. Okay, right. Next, let's try to solve the following task. I will use this 4, task number 4. Let it be the fourth derivative of y plus 2y2 primes plus y equals 0. Okay, let's try to solve. Okay, let's do it together. So it's lambda squared plus, lambda to 4, 2 lambda squared plus 1 equals 0. How to solve this equation? So I suggest to use the change of variables. I hope that it will work. Right. So let t be equal to lambda squared. Then we have the equation t squared plus 2t plus 1 equals 0, from which we have t equals negative 1. and this is a multiple root. Next, we have the following. If we substitute it here, we have lambda squared equals -1. What are the roots of -1? I and the conjugate -1, minus I, right? So two conjugate complex roots, and they have multiplicity 2 of multiplicity 2. So we will form two functions, e to the power, so 0. So if I will do it step by step. If lambda equals alpha plus or minus e beta, I will form two functions. Y1 will be e to the power alpha x cos beta x, and y2 will be e to the power alpha x sine beta x. And what about our case when lambda equals plus or minus I? Which functions should I form? What is alpha? It is 0. So e to 0 next times cos of which argument? 1. Cos x. So this means that it is just cos x. And y2 is sine x. So these are two solutions, but we have the fourth order differential equation. We need to find two more solutions, linearly independent solutions. What shall we do? Right, so we should take into account the multiplicity, of course. So as before, it is very cumbersome. It will involve very cumbersome manipulations. So, but as before, we can multiply. We can. It is possible to. So we can show that we must multiply cos x by c1 plus c2x. So y of x will be equal to c1 plus c2x times cos x plus c3 plus c4x times sine x. So if we have, as before, if we have a complex root with some multiplicity, so of multiplicity k, for example, what shall we do? Then we shall so we should form this solution and multiply it by the polynomial of the form c1 plus c2x plus dot plus ck to the power x to the power k minus 1. And we should do the same with the second solution. It will be equal to c1, let it be d1 plus d2x plus dot plus dk times x to the power k minus 1. Okay, is it clear? Well, okay, shall we go further? So I'd like to include non-linear parts. So I'd like to consider non-homogeneous equations, right? And our goal will be to study how to find the particular solution of a non-homogeneous equation. Right. Maybe we need a break, and after this we will continue. Right. Let's do the break. Let's have a break, and after this we will discuss non-homogeneous differential equations. Let's continue. First of all, I'd like to. So now I'm going to discuss the right-hand part of the non-homogeneous linear differential equation. I'd like to recall that it has the form equals q of x. Now I'd like to discuss the form of the function q of x. So do you know the functions that have finite number of linearly independent derivatives of any order? So functions having finite number of linearly independent derivatives. For example, let's consider function. So the types of functions. So functions, I will write it. Of any order. Okay, so let's start with the function y equals e to the power ax. Let's find the derivative. It is a times e to the power ax. So, and any other derivative up to order k will be equal to a to k times e to the power ax. Are these functions linearly dependent or independent? If we consider all these functions, are they linearly dependent or independent? Dependent. Right, so if a is any number, then these derivatives, all the derivatives are linearly dependent, of course, dependent. Because y prime equals a times y. So a is a constant. So y prime and y are linearly dependent. And all of the derivatives are dependent with, can be expressed in terms of y, right? So y, the k's derivative can be represented as a to k times y. So the k's derivative is linearly dependent on y. It depends on y, because this is multiplication by constant. Right. So we will consider this function. So q may have the form of e to the power ax. Right. So let's consider the function cos x. Cos may be bx. Let's find the derivatives. If we take the first derivative, y prime will be equal to minus b sine bx. What about these two functions? Are they linearly dependent or independent? Independent, right? It is easy to check that these two functions are independent. But if we take the second derivative, we will get, so the derivative of this derivative will be minus b squared times cos bx. But it is equal to minus b squared times y. So the second derivative depends on y. So the second derivative of y and y are linearly dependent. and the third order derivative is equal to also minus b squared times y prime. So the function cos bx has finite number of linearly independent derivatives. It has only one linearly independent derivative, this one. But all the other derivatives depend on y and y prime. Right? So we will consider these functions also. So, and if we combine these two functions, okay, so first of all, let's consider sine of bx. So this function also meets the requirement, right? It's the same as cos bx. So the first derivative is linearly independent, but the other derivatives will be linearly dependent. But if we combine e to ax and these two functions, will the new function meet our requirement or not? What is your opinion? If we consider the function e to ax times some linear combination, what about finite number of linearly independent derivatives?
I think only the first one will be.
Right, right. So, yeah. So this function also has a finite number of linearly independent derivatives. Only the first derivative will be independent, but the other derivatives can be expressed in terms of y and y prime. Yeah. Okay. Next polynomials. Next comes polynomial. If y is equal to x to k, for example. Right, so y prime is independent of y. Y prime will be k, x to k minus 1. These two functions are linearly independent. But the last non-zero derivative will be the derivative of order k. It is equal to k factorial. It is a constant, and other derivatives will be equal to 0. And so this function also has only finite number of linearly independent derivatives. They are x to k minus 1, and so on. Okay. So in what follows, we will consider the functions q of x of this form. So it should be the linear combination of functions having only finite number of linearly independent derivatives, right? So q of x must be a polynomial of x, polynomial of x, plus so the linear combination of the functions of this form, multiplied by x, of course, also. So plus, generally it can be represented as, just a moment, it can be represented as e to some power times p1 of x, a polynomial multiplied by cos bx, plus a polynomial depending on x times sine bx, plus the terms maybe, so the linear combination of the terms of this form. So we will consider these polynomials, and now we are interested. So we are interested in the particular solutions to this equation. It will be found using the method of undetermined coefficients. And today we will discuss case 1. When no terms of Q of x is alike some functions, some solution of the homogeneous differential equation. So it can be formulated more rigorously. So no term of Qx is the same as a term of yc. So I will write this. No term yc. Okay, and now I will explain what it means. So now let's consider an example, I think. So the method of undetermined coefficients, and I will explain it using the example. So this is task number 6. Find the general solution of the following equation. y2 primes plus 4y prime plus 4y equals 4x squared. Just a moment, I think. Plus 6e to x. Let's consider this differential equation. To solve this differential equation, we should complete 2 steps. So step number 1. So find yc, so the complementary function, which is a solution of a homogeneous, of a corresponding homogeneous equation. So this is step number 1. So we need to solve the characteristic equation. Lambda is equal to plus or minus 2. Then yc is equal to, so what, not minus 2. This is the multiple root, e to minus 2x times c1 plus c2x. Okay, this is step number 1. Next, step number 2. Now we will try to find a particular solution of this equation, of the original equation. And we will try to find it in the form, the following form. So first of all, you must compare this this function with the y complementary, yc. We have e to x here and e to negative 2x here. So these terms are not alike. They are not the same. And we have a polynomial here and no polynomial here. So multiplication by a polynomial doesn't matter. So we have no alike terms, no same terms. And so this is case 1, and we will look for a particular solution in the form of the polynomial of the second order. So with undetermined coefficients. So it will be ax squared plus bx plus c. So a polynomial of the second order, and plus all of its independent derivatives. linear combination of a polynomial x squared and all of its linearly independent derivatives. Well, plus next e to x, so some constant undetermined coefficient d times e to x. And now our goal is to find a, b, c, and d. How to do this? How can we do this? How to find a, b, c, and d? What is your opinion? What are your ideas? So a particular solution should have this form. So there are several particular solutions, but one of the solutions must have this form. How to find a, b, c, and d then? We should use the fact that this particular solution must satisfy this differential equation. So now our goal is to find the derivatives of this function and substitute the derivatives, the first and the second derivatives and the function, into this differential equation. Well, yp prime is equal to, we will differentiate, let's differentiate this. We will get 2ax plus b plus d e to x, and y2 primes p is 2a plus dE to x. And substitute these derivatives into the equation. I will recall it. So we will get 2a plus dE to x plus 4 multiplied by 2ax plus b plus dE to x plus 4 times ax squared plus bx plus c plus d. The dE to x equals 4x squared plus 6e to x. So now, is it clear? So I know the form of a particular solution, and I want to substitute it into the original differential equation because I know that it should satisfy this equation. So to do this, I need to find the derivatives of our particular solution and substitute them into the equation. Right? So I get this. I have obtained this equation. What shall I do next? I want to collect similar terms and to equate them. So let's collect similar terms. I have the terms containing e to x, this one, and this, and this. So if we collect these terms, we will get, so d plus 4d plus 4d, so it is 9d times e to x. This must be equal to 6e to x, and we will find d from this. It follows that d equals 6 over 9, so 2/3. Next, I will equate x squared, so the polynomial, right? I have a polynomial. It looks like 4ax squared. So only one term containing x squared, and it will be equal to 4x squared, right? So plus, next the linear term, not from here, so here I have a linear term 8a plus 4b times x. This is a linear term, and the constant term will be 2a plus 4b plus 4c, and it must be equal to 4x squared. Okay, is it clear? So collect similar terms. And we want these two polynomials to be equal. And so we should equate their corresponding coefficients. We have 4x squared and 4ax squared. So we have the following. 4a equals 4. Then the linear term. So this linear term, and there is no linear term. So this means that plus 0x plus 0. So this means that 8a plus 4b must be equal to 0. And at last, so 2a plus 4b plus 4c equals 0. So I need to solve this linear system from which I have a equals 0. Then if I 1, so sorry, if I substitute 1 for a here, I will get b equals 2 minus 2. And I want to find c. In order to find c, I must substitute 1 for a and negative 2 for b. And I will get 2 minus 8 plus 4c equals 0. So c will be equal to 6/4, 3/2. And now I know y particular. So y particular must be equal to ax squared, but a is 1, so x squared. Next, minus 2x plus 3/2 plus 2/3 e to x. This is y particular. So step number 2 is completed. And now the answer. So you can ask the questions if you have ones. So do you have questions? So maybe it's too difficult, right?
The answer is yc plus yp.
Right, and the answer is yc plus yp. Yeah, you're right. Yc is e to negative 2x plus yp is x squared minus 2x plus 3/2 plus 2/3 e to x. Well, so this is the answer. Okay. Now let's consider one more equation, and after this we will finish our seminar. So, but the idea of this procedure is not so complicated. Maybe it's difficult to find all the constants, but this is only algebraic manipulations. So to solve a characteristic equation, then to find the form for y particular, and after this find all the constants using the method of undetermined coefficients. Task number 7. Find the solution, the general solution of y2 primes minus 3y prime plus 2y equals 2x e to 3x plus 3 sine x. Okay, so step 1. We start with the homogeneous equation. And the roots are lambda 1 is 1, lambda 2 is 2. And so yc is equal to c1 e to x plus c2 e to 2x. So step 1 is completed. Now step number 2. First of all, we must compare the terms e to x, e to 2x. Compare them with the function in the right-hand side of the non-homogeneous equation, and we can see that no terms are alike. So this is the simplest case. Case number 2 will be discussed later in a week. So next week. Okay, step number 2. We will look for a particular solution in the form. So we should take this function, the linear combination of the function of the type x times e to 3x and its derivative and all the derivatives. So yp must be ax plus b times e to 3x. So this part comes from this term. Next we can see sine x, and we should write down this function and its linearly independent derivatives. The derivative of sine, the linearly independent derivative of sine is cosine. So we must write c sine x plus d cos x. Okay. And next, we should find these 4 coefficients using our equation, differential equation. So we need to find y prime. It will be equal to a. So if we differentiate plus 3ax plus 3b into 3x plus c cos x minus d sin x. Next, y2 primes p is equal to, so we differentiate, so 3a plus 3a, so it will be 6a, right? If we differentiate this or multiply, so plus 9b 9ax e to 3x minus c sin x minus d cos x. Okay. And next substitute this into our original equation. It will be 6a 9b 9ax e to the power 3x minus c sin x minus d cos x. This is y prime. Next, minus 3 multiplied by y prime. And plus 2y.
Very long.
Right, very long. Right, time equals 2x e to 3x plus 3 sine x. Okay, so we will combine these terms together. And from this, we have the following. So we may omit e to 3x because it is never 0. So we will get the equation 6a plus 9b plus 9ax. Next, minus 3a minus 9ax minus 9b from this, and plus 2ax plus 2b equals 2x. Right. So collect similar terms. 6a minus 3a, it will be 3a. Next, 9b minus 9b plus 2b, so plus 2b. Next, 9ax minus 9ax and plus 2ax equals 2x. From this we can see that a equals 1 because we have, so 2a is multiplied by x and 2, right? And 3a plus 2b equals 0. So b equals minus 3/2. So we are done for the first part. And for the second part, we must equate the sines, the coefficients of sine and cosine. So we have sines, this one, this one, this one, and this one. So for sines, we have minus c plus 3d. Okay, so plus 2c will be plus c equals 3. And for cosines, we have minus d minus 3c plus 2d, so plus cos x equals 0. So we have the following equations. So d equals 3c and c plus 3d equals 3. So this means that tan c equals 3 and c is 3/10 and d is 9/10. Okay, so we are done. We know yp. Yp is equal to 1 minus 3/2. So it's this times e to 3x plus 3/10. It was sine, right? Times sine x plus 9/10 cos x. And the answer y equals yc plus yp. Yc plus yp. So that so it will be c1 e to x and c2 2x and plus this. Okay, so that's all. Okay, thank you. Kathy is sleeping. It's very, very difficult. Thank you for your attention.
Yeah.
Okay, next time, next week, we will not have the recording, so I will make a recording from home. So I will be busy at this time. So we will not have a meeting in Zoom like now. Okay. Have a nice day. Thank you.